today I will have a talk about the manipulation of magnetic solitons under the influence of DMI gradient. Just a moment.
Sorry to interrupt you. Can you please go to the presentation?
Yes, just a moment. Okay. Okay, let me start because I'm not able to open them. Okay, so we will have a quick talk about a quick definition about solitons. Then we will. Okay. Okay, so we will have a quick talk about soliton. We will define together magnetic skirmings and vortices. We will talk about some recent soliton-based applications and some 2D materials hosting magnetic solitons. We will discuss together the equation governing the dynamics, in addition to the some results we get for the dynamics of solid skirmings and vortices. At the end, we will give a brief introduction into Hopkins and a simple simulation. So solitons are defined as solitons can be defined as in physics as a nonlinear localized wave packet. They were firstly discovered in 1843 by John Russell, and we can differentiate between several or different types of 2D solitons, including skirmings and magnetic vortices. And when mapped to 3D space, we can end up by magnetic Hopkins. The first theoretical prediction of the most popular or the most known 2D soliton, which is skirmia, was in 1998, and then, but the first observation was until 2009. It can occur or it can take place in different materials, including metal, semiconductor, insulator, bulk, and thin films. And the trick is that it is not only observed at low temperature, but only at room temperature. You can always engineer the size of skirmions, and it's usually observed in mediums or in systems that were characterized by out-of-plane magnetization and the DMI interaction. We can differentiate between two different types of magnetic skirmions, either a nil skirmion or block, depending on the DMI. If it's bulk DMI, so we'll end up by a block DMI having a vortex-like distribution of domain wall spins, or a nil one having a radial domain wall distribution of domain wall spins, and it's characterized by an integer skirmion number or winding number. And it's interesting because it can be created and manipulated by different or various means, including, for example, the magnetic field gradients, temperature gradients, anisotropy gradients, spin transfer torques, and it's characterized by its ability to react to ultra low electric current in order of 10 power 6. Now we move on to the second type of soliton, which is a magnetic vortex that is considered as a natural phenomena. And in magnetism, it was firstly observed in 2000 in circular thermal noise. And we can differentiate between two different types of vortices, either radial or circular, depending on polarity and chirality. And it's characterized by a non-zero winding number. Also, it can be manipulated as skirmions by different means. Since solitons are considered promising for technological applications, then we can have a quick example about it. We can talk about, for example, the skirmion-based artificial synapse for neuromorphic computing, and we have another example, which is the magnetic vortex racetrack memory. We have to mention that solitons, skirmions, vortices, and others showed an appealing results in the racetrack memory applications. Now, many 2D materials, due to the importance of 2D materials being highly flexible and known for its interesting thermal and electrical properties, we were interested in dealing with 2D materials, and especially the chromium triiodide material in our simulations, in addition to many other the existence of many other 2D materials that are silicon hosting and that are interesting, but we are concentrating on the chromium triiodide. And when dealing, when we want to study the dynamics of solitons, we have to, or they are governed by the Lindua-Lifshitz-Galbert equation, where the first term is the percussional term, the second term is the damping, and the third one is related to the spin transfer torque. And the energy here can be a combination of the exchange energy, the anisotropic energy, the magnetizing field, the external field, in addition to the DMI energy. That can be composed, as you said, into two parts, either the two types, either a bulk one or a interfacial one. And now, when we want to study the motion of solitons, then the core translation of solitons is governed by Thales' equation, where the full magnetization of solitons is usually given by or always given by the position of this soliton at each instant. So integrating the LLG equation, we can end up by the Thales equation, where here G and D are considered as the geotropic and the viscosity tensors. G is directly related to the topological charge, and D is related to the motion of the soliton along the direction of the applied field. Okay, now in our simulations, we considered two ferromagnetic materials that are coupled interferomagnetically via the RKKY interaction and separated by a non-magnetic spacer. We considered two types of materials: cobalt iron boron and chromium triiodide. And in both materials, we studied both nil and block skyrmions. And the aim of the study was to get the dynamics only under the effect of the DMI gradient to end up by a low power manipulation with no external field and no applied current. We considered two geometries, circular and square, but due to some limitation, we are going to discuss only the square sample. We get the DMI stability domain DMI stability domain by micromagnetic simulations, and they were confirmed by theoretical predictions. Okay, so first, since the COFAB material or the dynamics were already studied or analyzed in literature, we will show the results just of a chromium triiodide. We're considering only a single layer. We see that the block and nil skyrmion will move along the positive X and Y directions, where the X direction, where along the X, the skyrmion is moving along the DMI direction, and along Y, this motion is due to the Magnus force. And we see that with increased damping, the velocity component with higher damping constant, then we will end up with a higher velocity component. Now, considering the antiferromagnetically coupled layers, which means considering a synthetic antiferromagnet, SAF, we see that in this case, since they are antiferromagnetically coupled, then the topological charge will be 0, and then the Magnus force will be neglected. So the skyrmions will move along a straight line along the direction of the applied gradient. The same mechanism or the same simulations were performed also in case of circular and radial vortices. We considered here also two geometries, a circular and a triangular strip. In case of triangular strip, also we considered these two materials, and we get the stability domains of both COFAB and chromium triiodide. We were able to get the stability domain of both materials, but in case of circular vortices in 2D material, we were not able to stabilize the vortices. No stability range was observed, and we observed that both in case of skyrmions and vortices, the stability domain is lower in case of 2D material, which means that stability can be easily attained in case of the 2D material, which means that skyrmions and vortices can be manipulated easier in these materials. Now, concerning the dynamics of radial vortex in single layers of COFAB and CRI3, we see that they share somehow similar dynamics, so that the translational motion is observed under the effect of DMI gradient, and the velocity also depends on the damping coefficient. So they share similar dynamics with the skyrmine, but the only difference is that here the radial vortex move mainly along the positive x direction with a negative movement along the y-axis. Considering SAF, we see that the radial vortex will move also with zero Hall effect or zero Hall angle due to the fact that also the topological charge is neglected. Okay. Whereas in case of circular vortex, we see that starting by a circular vortex will end up by a uniform state, and this is due to the fact that we were not able to stabilize the vortex, the circular vortex, at any DMI range, and this end up by an explosion dynamics. So we can say that the circular vortex undergo expulsion, so expulsion dynamics under the influence of linear IDMI gradient. And this mechanism is interesting in applications, spintronic applications, including, for example, diodes. Now, when projecting this 2D solitons into a 3D space, then we'll end up by a 3D topological soliton known as Hopfian. That is what was first proposed by Ludwig Fadeev. And it's known by its non-zero Hopf index. It is observed in some multi-layers and chiral magnets and ferromagnets. And here we see how it's observed experimentally, and it is confirmed by simulations. Now also we can, in case of 3D solitons, we can differentiate between two types of solitons, either a nil type or a block type. And the advantage of Hopfian over skyrmine is that the interactions needed to stabilize or to end up by manipulating or creating Hopfian are much weaker than those needed in case of skyrmines. Okay, also many perspective or paradigms are being used in order to manipulate and create and stabilize Hopfian, like current magnetic fields, spin transfer torques. Now here I show also we have to announce that Hopfian, the dynamics of Hopfians are also governed by motion similar to the 2D solitons, and also the motion is governed by Thales equation, but the gyrotropic tensor is always neglected due to deformations in case of Hopfians, so always it's neglected. And here we show just a simple simulation in order just to compare between the dynamics of skyrmine, a 2D and a 3D soliton. We considered a system composed of a Hopfian state sandwiched between two states with high magnetic anisotropy. And we see that under the effect of only DMI through gradient and the absence of any external fields and currents, the Hopfian will move along the positive x direction in the same direction of the applied field. And this is expected because the topological charge is also here neglected. And that's all in summary. So we performed a systematic study to study the effect of linear gradient on skyrmions and radial and circular vortices, in addition to Hopfians, and we show that the stabilization of this magnetic configuration can take place for specific intervals of DMI in the absence of any external fields or currents. And under the effect of DMI gradient, the skyrmions and radial vortices move with a damping dependent trajectory. For in case of an SAF, a zero Hall angle leads to a linear motion in all the topological textures. And thank you. That's all.
Thank you, Rayan, for the nice talk. Now the floor is open for the question. You can raise your hand or write in the chat box if anybody has any question. If not so, then I would like to ask one question from you. So what is the ideal system to host the hafnium in that particular stack? Like, is there any ideal system like this ferromagnet layer and then this layer or something like that?
Okay, most systems that are, okay, so as I said that chiral magnets and multi-layers, especially multi-layers, are the best systems to host the Hopfians. And yeah. It's
So
it's
here,
mainly in multi-layers. Yeah.
here is one question. You can unmute and ask the question.
Hello, can you hear me? Hello?
Hello.
Yeah, I have a question regarding your simulations. What kind of package or code do you use in order to simulate?
Oh, okay. The code used is the micromagnetic computation were performed by using a state-of-art code, which is Betaspin, that is CUDA native, and yeah, and it used the Adams solver in order to solve the LLG equation. Yeah.